Welcome to Introductory Chemistry with Dr. H. This is a content video about intermolecular forces, particularly phase changes. First, what I'm going to do is help you develop your sense of the molecule level or atom level picture of what phase changes are. Then I'm going to talk about vaporization and condensation and how that relates to energy, and we're going to talk about a quantitative way of thinking about those relationships. Then I'm going to talk about melting and freezing and the energy associated with those phase changes, and then sublimation and deposition and the energy associated with those phase changes. And then finally what I'm going to do is I'm going to kind of put all of those phase changes on one diagram in the form of a heating curve and talk about the energy associated with different parts of that heating curve. So that's where we're going today. So intermolecular forces and phase changes. You've already probably started to develop a sense of what's happening at the molecular atomic level in solids, liquids, and gases. In solids, the molecules are very close together. There's a strong role of intermolecular forces. Each atom in a solid is held fixed in space by strong intermolecular forces to its neighbors, right? In a liquid, those intermolecular forces are still in play. It's a condensed phase. The atoms or molecules are able to move around, but they're still making lots of contacts with other neighbors, and so they're having strong attractive forces which keep them from flying off, right? And so in the gas, that's when we've, say, heated up a liquid and given those molecules or atoms enough energy to break out and basically to break all of the intermolecular forces that exist between the atoms or molecules, and they have high kinetic energy and they're moving rapidly and there's lots of space between them, right? So that's our picture of what's happening. And we tend to see solids when the pressure is high. So if this green line indicates pressure, as the pressure increases going down, when you add pressure to a gas, you force the atoms or molecules closer together, it'll eventually liquefy. If you keep adding pressure to a liquid, eventually you'll force the atoms or molecules even close together into a rigid arrangement, and it will solidify. So increasing pressure will increase the likelihood that you have a solid for any given material you're talking about. Similarly, if you take temperature and you cool it down, so low temperatures favor solids because there's very little kinetic energy for the atoms or molecules of that material to move around, and so the intermolecular forces are able to hold them in a rigid lattice. And as you warm them up, the warmer it gets, the more likely you are to liquefy, right, through melting, and then you form a gas. So there's this relationship between temperature and pressure and the phase of matter, and different materials, elements have different properties regarding these things. So let's talk specifically about what we call these different processes. So when you're talking about a solid going to a liquid, we call that melting, right? So this is melting. And when we have a liquid and it becomes a solid, right, we call that freezing. Okay, so those are words associated with those lines right there. And so we're talking about these two processes here, where we melt going this direction and we freeze going that direction. When you melt something, you have this sense that you have to add some energy. And the reason why you have to add energy to the system is you need to give those atoms or molecules a little bit more kinetic energy to break away from those intermolecular forces that are holding them fixed in the lattice, right? And so it makes sense we need to heat it up to melt a solid. We have that sense, say, from ice, right? And if you want to take a liquid and you want to form a solid, we know that we can take energy out of the system, right? We can pull energy out, and the intermolecular forces then are able to take those molecules and atoms that are moving around a little bit. As they move around less, they're locked into a lattice in the form of a solid. Okay, so we also know that we can evaporate or vaporize a liquid by heating it up, right? So we have this process called vaporization. And then we have the reciprocal process called condensation. Okay, so we have condensation and vaporization as reciprocal processes again. When you have a liquid, in order to get an atom or a molecule in a liquid out into the gas phase through vaporization, you have to give it a lot more kinetic energy so that it can break all of the intermolecular forces that are holding it into that liquid, and then it has high kinetic energy to move around, and it really doesn't interact with other particles. And when you want to condense something, like think about the condensation on a glass of water on a summer day, you're taking energy out of the water molecules that are in the air. And as the water molecules slow down and they encounter one another, those intermolecular forces are now strong enough to hold them in the liquid, right? So we have these reciprocal processes of vaporization and condensation, okay? And the one that's a little, the pair that's a little less familiar to us is the direct change between a solid and a gas, okay? And so if you have something like dry ice, and perhaps you've seen this before, dry ice doesn't have a liquid phase at atmospheric pressure. So it goes directly from solid, very cold carbon dioxide, directly to the gas, right? And we call that sublimation. Sublimation. And the opposite also happens if you cool down carbon dioxide at around atmospheric pressure. What's going to happen is it's going to skip the liquid phase and it's going to go immediately from the gas to the solid, and we call that deposition. Okay, deposition is the name of that process. So here what we're talking about, sublimation, is this process going straight from the solid all the way to the gas. So you have to give the atoms or molecules in that solid enough energy to break out all the way into the gas phase. And conversely, deposition is when you're taking a lot of energy out, or you're adding a lot of pressure, crunching those atoms or molecules together to force them directly into the solid. All of those things are processes that occur readily in different materials. And that's what we're going to talk about today. So there we are. So I want you to have a good sense of how intermolecular forces play into each of these processes, right? The intermolecular forces are the things that are holding the atoms and molecules in these condensed phases, and they're the reason why we have to add energy to move them, say, out of the lattice into liquid, or out of the liquid into the gas phase, okay? Intermolecular forces are really key to these processes of phase change. Okay. So let's talk about vaporization and condensation, these sort of reciprocal processes. As we've already been talking about, intermolecular forces are important in this process, and I kind of have a little detail of vaporization and condensation here. Vaporization is the pink arrow, taking atoms or molecules out of a liquid. So this is supposed to represent a liquid. So these atoms and molecules are moving around, but they're not able to break away from one another. So they're remaining in a condensed phase. If you provide enough energy, or you reduce the pressure enough, you can give them enough energy so that they can break out of the intermolecular forces. They're holding them in the liquid, and then they can move around, and they really don't interact very much with other atoms or molecules. So if this phenomenon, I mean, all liquids, a certain number of the atoms are going to have enough energy to break out. And the weaker the intermolecular force is, the more atoms will make it up into the vapor phase. Whenever you have atoms in a vapor phase, that creates pressure because those atoms are going to collide with the walls of the vessel. So if intermolecular forces are weak, so if intermolecular forces are low, what we see is that the vapor pressure, the pressure that the liquid exerts on the vapor above it, is higher. Conversely, if intermolecular forces are very strong, the vapor pressure is quite low. So that's an important relationship to keep in mind. Vapor pressure is that pressure that a liquid produces in the vapor above it. And regardless of the temperature, regardless of the setting, liquids are always pushing some of the atoms or molecules out into the vapor phase. And the weaker the intermolecular forces, the higher that pressure is. So what's the relationship between vapor pressure and temperature? Well, as you heat up a liquid, all of the atoms and molecules in that liquid have, on average, a higher kinetic energy, and more of them are going to have enough energy to break away. So if there are more atoms or molecules moving into the vapor phase, that means there's going to be an increased pressure. So if you increase the temperature, you expect the vapor pressure of that liquid to increase. So there's this relationship between temperature and the pressure above the liquid. Conversely, if you cool it down, you're taking kinetic energy out of the atoms that are in the vapor phase, or the molecules that are in the vapor phase, and more of them are going to succumb to the strong intermolecular forces, or even the weak intermolecular forces in the liquid. The cooler it is, the easier it is to hold those atoms or molecules in the liquid, and the vapor pressure will go down. These sort of intuitive relationships are really important to keep in mind. So there's another term that you need to sort of get familiar with, and that's boiling point. Boiling point, right, is the temperature at which something boils at a given pressure, okay? And so if you think about it in terms of vapor pressure, boiling starts to occur when the vapor pressure of the liquid equals whatever the external pressure is, whatever the pressure in the room. Let's just say it's 1 atmosphere. So when you've heated a liquid enough so that it has a vapor pressure that's equivalent to the external pressure, it's going to start vaporizing the atoms and molecules that are in that liquid. So they're going to start moving into the gas phase in an equilibrium way. So this is an important definition. The boiling point is the temperature at which the vapor pressure is equal to the external pressure, right? And so if the external pressure goes up, conversely, this is another relationship here. If the external pressure goes up, what's going to happen to the boiling point? What do you think? So if the vapor pressure goes up, you're pushing atoms or molecules back into the liquid, right? The boiling point, it's going to require a higher temperature to get them out, right? So if the external pressure is up, the boiling point is also going to go up. If the external pressure goes down, that means it's going to be easier to eject an atom or molecule from the liquid, put it out into the vapor phase. That means the boiling point's going to go down. So a practical thing that you might know about, if you go up into the mountains and you boil water, it boils at a cool temperature. And there are real impacts of that. For example, if you want to cook pasta while you're hiking in the mountains, you have to cook it for longer because the boiling water that you're cooking it in is actually cooler. The boiling temperature of water is cooler when the pressure is lower. Okay, and so that's because of this relationship between boiling point and the vapor pressure of a liquid, and we're talking about water. Okay, so we've got this sort of qualitative sense of vapor pressure, and we also have this sense that the pressure above a liquid is related somehow to the temperature of that system. And so Clausius so let's take a look at some examples. So let's first talk about intermolecular forces. So here are some examples of some boiling points at 1 atmosphere of some substances. So argon has a boiling point of minus 186 degrees Celsius. We know from our study of intermolecular forces that the strongest intermolecular force in argon is London forces. Okay, and one way that we can think about how much or how little energy is required to vaporize, to take from the liquid to a gas, some material, is what's known as the heat of vaporization, or delta H VAP. This heat of vaporization is the amount of energy you have to put in to move a mole of atoms from the liquid phase or molecules in liquid phase into the gas phase. And for argon, with very weak intermolecular forces, the strongest intermolecular force in argon are London or dispersion forces. It's 6.3 kilojoules per mole, a fairly low vaporization energy. Okay, so if we talk about something like diethyl ether, this molecule we know has dipole-dipole forces, right? It doesn't have hydrogen bonding. There are no oxygen, nitrogen, or fluorine hydrogen bonds, but it does have a net dipole in this molecule. And you'll see that the heat of vaporization, the energy required to vaporize a mole of ether, goes up substantially to 26 kilojoules per mole. And also, as you would expect, the boiling temperature goes up. The vapor pressure of ether is lower than that of argon. And so you have to heat it up higher for the vapor pressure of ether to equal the external pressure. So dipole-dipole forces are stronger intermolecular forces. When you I picked 1-butanol as the next thing on the table because 1-butanol is an isomer of diethyl ether, meaning it has the same molecular formula, the same molecular weight, and basically the same shape. But we recognize that butanol is capable of hydrogen bonding, right? And we know that hydrogen bonding is the strongest intermolecular force and that it's much stronger than just dipole-dipole forces. And what you see is a jump in the heat of vaporization. It takes more energy to move a mole of N-butanol from the liquid phase into the vapor phase. And you also see a tremendous jump in the boiling point. That means in order to get the vapor pressure of 1-butanol to 1 atmosphere, you have to heat it a lot hotter than ether, right? Much hotter. Okay, and now let's do kind of a more extreme case. Mercury metal, which is a liquid at room temperature. Mercury metal has a heat of vaporization of 59, very high energy to remove a mole of mercury atoms from liquid mercury into the vapor phase. You can vaporize it, but you have to heat it up to 357 degrees C. That's the temperature at which mercury would boil. And we know that the bonding or the intermolecular forces in a pure metal, are metallic. They're metallic forces, and we know those to be strong forces, very strong intermolecular forces, the top of our table of intermolecular force strength. So the heat of vaporization is a measure of the energy that it takes to do this process, and it reflects intermolecular forces, and we can relate it to an energy, and we can relate it to the boiling point of that material. Okay, so now let's talk about the Clausius-Claperyon equation. The Clausius-Claperyon equation is a mathematical way of expressing this idea that there's a relationship between pressure and temperature, right? So as the pressure or as the temperature goes up, right, when we heat up a liquid, we expect that the pressure of that liquid is going to increase, right? And so this is the relationship Clausius and Clapeyron figured out. So as we heat up a liquid, right, as we increase its temperature, so here's temperature, 1 over T becomes a smaller number. Notice that there's a negative sign here, so that whole right side becomes less negative as the temperature goes up. And that means that the pressure is going to increase. The natural log of P will increase as the left side becomes less negative, right? It's a 1 over T, so it's becoming less negative. So there's this kind of reciprocal relationship between temperature and pressure. And it relates to the energy that's required to vaporize a mole of that atom or molecule. So the heat of vaporization plays in here, as does the gas constant R, right? And so this is the Clausius-Clapeyron equation. We really don't use it very often in this exact form because C is undefined, and C is going to depend on a number of things, including the units of pressure that we decide to use. And so much more often what we do is we use the Clausius-Clapeyron equation in a comparative form. That means you can check your textbook and see the derivation of going from this equation to that one, but this is the same equation written to relate the pressure and temperature, the known pressure and temperature at one condition to the pressure at some other temperature. So for example, at some temperature, we know the pressure, right? If we wanted to know what the pressure was at a second temperature, we could plug that information into this equation. I'm going to do an example in just a second. So this allows us to take information we know about a liquid and derive information at another temperature or under another pressure, depending on whatever we're after. So this is the relationship between temperature and pressure, or temperature and vapor pressure of a liquid. And so units are important here. So the gas constant, we're going to use it in the form of 8.314 joules per Kelvin mole. What that means is we have to convert all of our temperatures to Kelvin so that we're in the same units. Usually when we look up delta H's of vaporization, they're in kilojoules per mole, so we need to multiply those numbers by 1,000 to make sure they're in joules per mole so that the units match the R constant. So when we do this division, we haven't introduced any extra powers of 10 on the top or the bottom. And these pressures here, they can be in any unit you want as long as the unit on the top, P1, is the same as the unit on the bottom, either millimeters of mercury or atmospheres or whatever. As long as it's the same, it's okay because we're dividing them and the units have got to cancel. All right, so let's see how we might apply this idea. So we know that, or we could look up, that the boiling point at 1 atmosphere of pressure of ethanol is 78.3 degrees Celsius. And what if we wanted to know what the vapor pressure of ethanol is at 35 degrees? Well, we know that the boiling point is defined, right, as the temperature that the vapor pressure equals the external pressure, right? And we're told that the boiling point at 1 atmosphere, so that's the pressure, so we'll call that P1, is going to be 1.00 atmospheres, right? And T1 is going to be this temperature, right? So T1 is going to be 78.3, but we know that we have to put it into Kelvin, so that's going to be 351 273.45 Kelvin. Okay, so you just add 273.15. So there's our P1, T1. And what we want to know is we want to know what the pressure is going to be when we cool it down to 35 degrees C. So if I take 35.0 degrees C and add 273.15, I get 308.05. Okay, and so just to make sure we're keeping track of sig figs, this is where the sig figs are. 308.05 Kelvin. Okay, and we're assuming that this 1.00 atmospheres, that we're going to have 3 significant figures in that number. We know that we have this gas constant up here that's 8.314, and this is in joules per mole Kelvin, right? So I'm just collecting the things that we know. And the heat of vaporization of ethanol is something that we would have to look up. And so when I look it up, it says it's in the table, it's 39.3 kilojoules per mole, which is the same as 39,300 joules per mole Kelvin. Okay, and we have 3 significant figures in that number as well. So what you can see is we have all of the numbers in the comparative version of the Clausius-Claperyon equation, except the second pressure. So now what we have to do is we have to do some very careful plugging and chugging and careful tracking of significant figures. And because significant figures are a little bit tricky to track, what I would recommend is doing this piecemeal. So let's handle first what's inside the parentheses there with the temperatures. We've got a subtraction, and that follows one sort of form of sig fig rules, right? And subtraction and addition, it's however many places after the decimal are significant in the number that has the fewest significant digits, right? So there's that rule. And then in the bottom of that, we've got the multiplication rule. So in multiplication and division, it's the number going into that quotient or that multiplication that has the fewest sig figs overall. It doesn't matter sort of how many decimal places, right? So we've got different rules to follow. So let's kind of do this separately. So if I subtract 308.05 from 351.45, knowing that each of those numbers really has 4 sig figs, just 1 sig fig after the decimal place, that means the number that results can only have 1 sig fig, and I get, and you know, maybe I'm wrong, I've just done this math, so I think what I see is that's going to give us 43.4 Kelvin, and there really is nothing else beyond it, and that 4 is our significant digit. That's our last significant figure. So the number has 3 sig figs. And then when I take the quotient, I'm going to get a big number, so I'm going to use scientific notation. My calculator gives me 1.0826, and there's like a 4 after that, and then it's times 10 to the 5th. And because I'm multiplying two things that have Kelvin as units, it's Kelvin squared. Now both of those numbers had 4 sig figs, so this product is going to have 4 sig figs. So I've got a number there that has 4 significant figures, and then I can just do that division, and I know that when I'm doing a division problem, now it's the number that has the fewest sig figs. So I'm going to end up with three sig figs in my answer here. So if I write out what my calculator gives me, it's 4.0087 times 10 to the minus 4th, and one of those kelvins cancels. So I'm going to end up with 1 over Kelvin as my unit, and this number right here is the significant figure. So if this was the end of the problem, I would put a 1 there because I would round up. And so there we are. So that's what's inside the parentheses, and I would just save that number in my calculator with all the sig figs there, with all the digits it spits out, but we got to keep track of which ones are the sig figs. And so now let's do sort of the delta H vaporization over R part. So, this is going to be 39,300 joules per mole Kelvin, right? And we're going to divide it by 8.314 joules per mole Kelvin. Actually, yep. So what's happening here is that the units are canceling, and they must, because we've got like a natural log on the other side. So we need to have a unitless thing come out of there. Oh no, this is wrong. So it's just joules per mole. That I knew we had an issue here because we have to cancel the unit in the other term there, right? So here we go. So I've got the units right. I just copied them over wrong. So the heat of vaporization here does not have a Kelvin. It's just joules per mole. That makes more sense. Joules per mole. All right. So here we are. When I crank that through, what I get is 4.7269 times 10 to the third Kelvin. And because I have 3 sig figs in that top number, and this is a multiplication, that would be both of those numbers, the top and the bottom number there, both have 3 significant figures. All right, so there we are. And I'm going to continue with this on the next page because I'm already running out of space. So those are the numbers that we've got. And so now what I'm going to do is I'm just going to take those numbers in my calculator and I'm going to crank them together. Okay, and so when I do that, I get 1.89489 as it turns out. When you multiply those two numbers together. And because, again, we had 3 sig figs in one number and 3 sig figs in the other, this one is also going to have 3 significant figures, and there are no powers of 10 here. And that's the number that is actually going to equal the natural log of the pressure at temperature 1 that's going to equal the ratio of pressure 1 over pressure 2. So we'll say 1.89489 is going to equal ln of P1 over P2. And so now what we have to do is we have to like somehow figure out how to get those pressures out. So when you have a natural log, in order to sort of get rid of the log, you have to do the anti-log. So it's going to be E to both sides. Now the tricky thing about doing E to both sides is that we're going to have to figure out what happens with the sig figs. So one way we could write P1 over P2 is it's going to be E to the 1.89489. And we know that we have 3 sig figs in that number, 1.89. So what is the rule that tells us what the result is? When we plug it into our calculator, what is the rule that tells us what the result is? So I have the rule written here about how to handle sig figs of logarithms. So if you say have 4.2 and you take the logarithm of it, the number 4.2 we know has 2 significant figures. When you take the natural log, the number of sig figs in the original number becomes the number of significant figures after the decimal in the result. So in this in the result number here, it would be the 3 would be the last significant digit because it's 2 sig figs after the decimal. So if this were the final answer, we would say the answer, natural log of 4.2 with sig figs, is 1.44. That 4, rounding up from 3, because you have a 5 following it, would be the last significant digit in the number. Conversely, if you're taking the anti-log, it's the number of digits after the decimal in the thing you're taking the anti-log of. So if you're taking the anti-log of 1.44, you take e to the 1.44, you get an answer of 4.22, and there are other digits. But you know that the total number of significant figures in the answer is the number of significant figures that follow the decimal place in the thing that you took the anti-log of. So the answer would be 4.2, right? So you can see that this sort of makes sense because if you have 2 sig figs in the original number and you do the logarithm, you end up with 2 sig figs after the decimal place going that way. Or if you're taking the anti-log, it's the number of significant figures after the decimal place of the thing you're taking the anti-log of that ends up in the final answer. So now we got to sort of apply that here. What we know is we're taking the anti-log of 1.89, and so that means we're going to have two significant digits in our answer. So when I take e to the 1.89489, I get 6.65187. We see that we have the natural logarithm is 1.89, and that means, and the 9 is the last significant digit in that number, that means we have 2 sig figs in the resulting antilog. And so 2 sig figs would put the last significant digit right there on the resulting number. Now we're going to carry through all the significant digits, so you can save that number in your calculator if you want, and then we'll adjust by rounding at the very end of the problem to the correct number of sig figs. So if we want, what we're after, right, is we're after the pressure 2, the pressure at this lower temperature. Since we're after pressure 2, so we can solve this equation by multiplying both sides by P2 and dividing by this number, 6.65187, where the 6 right there is the last significant digit. And we can just do that calculation, and what we end up with, and I'm going to write more sig figs than we need and then just round to the right number of sig figs, is 0.15033. So and because we used atmospheres, P1 is 1.00 atmospheres, just to make sure you're clear on that, since I didn't copy this over from the previous slide. So if you take 1.00 divided by 6.65187, what you get is 0.15033 atmospheres. So with sig figs, that answer, so this is ATM, with sig figs, the final answer would be 0.15 atmospheres. And so, like you should always do with the problem, is to make sure that it makes sense. So if this liquid, ethanol, boils at 78 degrees, that means at 78 degrees, it's going to have a vapor pressure of 1 atmosphere. And if we decrease the temperature, we expect the pressure also to go down. So if we move the pressure or the temperature down to 35 degrees C, we expect a lower pressure, and indeed we see a lower pressure. P2, as it turns out, is 0.15 atmospheres with sig figs. So it takes a lot of care dealing with the significant figures and making sure you've got the math right, but this equation is very useful because it relates the pressure of a liquid at one temperature to the pressure of that liquid at a different temperature, right? And you always know that at the boiling point, the pressure is whatever the pressure that boiling point was measured at. So if most boiling points are measured at 1 atmosphere of pressure, you already know one set of pressure and temperature, because that boiling point is that temperature. So this is how you use the Clausius-Claperyon equation to relate pressure and temperature of a liquid. Okay, so this was the sig fig slide. So let's talk about melting and freezing for a little bit. So just to remind you, when you're melting, you're taking atoms or molecules that are tightly held in a lattice and you're giving them enough kinetic energy to start moving relative to one another. They still have lots of intermolecular forces between them. You haven't broken them away from all the intermolecular forces, but you've given them a lot more motion. So this, also depends on, the intermolecular forces. The energy required to do that process depends on the intermolecular forces. And we use a term called the heat of fusion, and that's the heat of melting, how much heat's required to take 1 mole of a molecular atom in a solid to 1 mole in the corresponding liquid. And we saw, this is the same set as before. Argon only has London forces, which are relatively weak. It has a low heat of fusion, meaning it doesn't take much energy to move from the solid to the liquid. It also has a very low melting point, so the temperature at which this occurs is quite low, right? It doesn't take much kinetic energy. Ether, right, we said had dipole-dipole forces, which is a stronger force. It has a correspondingly stronger, higher heat of fusion, takes more energy to move atoms, or in this case molecules, out of the solid into the liquid. And the temperature is also substantially higher, -116, right? So closer to 0. 1-butanol has hydrogen bonds as its strongest intermolecular force, right? So connecting back to intermolecular forces, its heat of fusion is higher, 9.2 kilojoules per mole, and corresponding increase in temperature of the melting point. Even though these two are isomers, the intermolecular forces are stronger when they're hydrogen bonds, so the melting point goes up to -89.8. And mercury, our example of metallic intermolecular forces, very strong intermolecular forces, the heat of fusion is much higher, 23.4, going from solid mercury to liquid mercury, and that occurs again at a higher temperature, so -39 degrees C. So that's how the energy is related there. Okay, so finally, this kind of weird case, sublimation and deposition. Sublimation, remember, is taking a molecular atom out of the solid directly to the gas. And so the heat of sublimation is how much energy it takes to take a mole of molecules or atoms in the solid to a mole of the gas. And it makes sense, but that heat of sublimation is just the sum of the heat of fusion and the heat of vaporization. So if you have the heat of fusion and the heat of vaporization, and you want to know the heat of sublimation, you just add them together. So there's nothing new to talk about in this other than it's a simple relationship at a given pressure. And likewise, you're going to release that much energy as you go from you have to, if you want to think about it, you have to cool the atoms down, remove energy from the gas phase to go all the way back to the solid if you're doing a deposition. So you've got to remove energy or cool it down. And the amount of energy you have to remove is just that heat of sublimation. You've got to pull that energy back out to put it back into the solid. Okay, so that's sublimation and deposition. So heating curves are a way we can sort of think a little more quantitatively about the energy it takes to move something through its various phases of matter. So what I want to do is I just want to walk through this heating curve. And particularly importantly, what I have on these axes is this is the temperature. This is the temperature on this y-axis, and time is on the x-axis. But what I want you to understand is that time corresponds to or is proportional to the energy that's been added or the heat that's been added. So the way these experiments are run is you have a coil, like an electrical coil, and you're passing a certain amount of electricity through that coil, and it's being converted into heat. And so you can measure how much heat you've been adding, and since the current through that coil is the same at all times, it's putting in the same amount of energy for every unit time. So every minute it's adding a certain number of joules of energy to the system. And so the longer it takes to move through a process, that corresponds to more energy that was required for that process. And if you monitor the temperature, say, like let's say we have a block of ice and the coil is embedded in the ice, and that ice is below its freezing point, below its melting point. So let's say it's at -10 or -20 degrees Celsius below. The first thing we have to do before it's going to start to melt is we have to actually heat that solid up to the melting point. And so that's what this line segment describes. It's heating the solid. The solid starts out below the temperature of its melting point, and you have to put in some energy. And so this progression of time shows that we're adding energy, adding energy, adding energy. As soon as the solid ice is at 0 degrees Celsius if it's water, now what we have to do is we have to put in that heat of fusion. We have to take the atoms that are in the solid and move them into the liquid phase. During that time, all the energy that we're adding is only going into that phase change, and none of it is changing the temperature. All we're doing is taking atoms out, or taking molecules of water out of the ice and putting it into liquid water. And so for a little while, what you observe is the temperature doesn't change, because this is the process of melting right here. In this you have solid here in equilibrium with the liquid. There's going to be both liquid and solid during that phase of the process. As soon as all of that solid is consumed and it's all liquid, now when we put more energy in, what we start to do is heat that liquid. And so on this leg of the diagram, what we're doing is we're heating that liquid. We're heating it up until the liquid is at the temperature of the boiling point. So it starts out at 0 degrees. If this were water, you're heating it up to 100 degrees Celsius. That takes a lot of energy to heat cold water to warm water. Once the water gets to the boiling temperature, now what you're going to do is you're going to start converting that water into steam, into gas, right? Into vapor water. And that takes a lot of energy yet, because now we've got to pluck those water molecules out of the liquid and relieve them of all their intermolecular forces, give them enough energy to break away from all intermolecular forces. And so that energy is being applied here. So this is heating the liquid water. So this is when there's liquid water that's in equilibrium with vapor water or steam. So I should write G here, right? Because it's like liquid in equilibrium with gas. So there's the liquid phase and the gas phase. This thing doesn't have to be for water. It can be for any substance. Once we get to this point right here, all of the liquid water is gone. So now you just have a container of steam. And if you keep adding energy, you can make that steam hotter than the boiling point of water. So this is superheating that steam. It's heating it up even higher. So if we want to think quantitatively about this, you learned earlier in your study of chemistry how much energy it takes to change the temperature of a solid or a liquid or a gas. And that has to do with its specific heat. So I've got the equation for that right down here. So if we start in the solid has a specific heat, right? Intermolecular forces are really important in there to determine that specific heat. The mass of the liquid is important, so we multiply the mass times the specific heat times the change of temperature that we need, right? So this would be where the delta T is found, right? So if we started at minus 20 for ice, we would have to get it to 0 degrees before it would start to melt. So the delta T would be like, whatever that temperature change is. Minus 20 to 0 is 20 degrees. Delta T is 20. We could calculate the amount of heat required, the amount of energy required had to be added for that segment. Then in this segment right here, what we know is we're taking atoms in the solid and we're putting them into the liquid. And that relates to this energy we just learned, the heat of fusion. And so the heat of fusion is a molar quantity, so it's the number of moles of whatever that substance is times that molar heat of fusion. That would tell you how much energy is required for that segment. Then once you've got all the liquid, if we want to know the energy that's associated with that next segment, it's the specific heat of the liquid. If we're talking about water, that would be liquid water times the mass of liquid water times the change of temperature that you're going to carry it through. So if we're talking about water, that's 100 degrees. We've got to take it from 0 all the way up to 100 degrees Celsius. So delta T would be 100, the difference in temperature from the start to the end. Then we have all liquid water, and we have to move it into the vapor phase. The energy associated with that is a molar heat of vaporization. So we would find the moles of water involved, or the moles of whatever involved, times its heat of vaporization. That's the energy that would have to be added in that segment of the heating curve. So we know that it takes more energy to, say, break a molecule of water out so it has no intermolecular forces in steam. It takes more energy than, say, taking a water molecule in ice and just giving it a little more flexibility in the liquid phase. So notice this segment of the line is shorter because it took less energy to go from solid to liquid as it did to go from liquid to gas, which takes a lot of energy because you're breaking all intermolecular forces. So then once you have gas, if you continue to add energy, what you're going to do is heat the gas, the steam. And so now you need the specific heat of the gas, which all these things are in tables, you can look them up, times the change of temperature that occurs. So what I'm saying is you could start any place on this curve and calculate how much energy it takes to get any other place on this curve, right? So if you started with a slushy that has water and ice in it, and it's 50% liquid, 50% solid, you're kind of starting in the middle of that. You could measure the mass of that, and you could know how many moles of that you have, and how much energy it would take to heat it up and vaporize your slushy, right? You could say how much energy would it take to take the water in that slushy and turn it all to steam at 120 degrees Celsius or something. You would just simply add up the energy you add at each segment of this line. So I'm not going to demonstrate that. It's just sort of being very careful with significant figures and plugging and chugging carefully. But the math is just an addition of different terms. And I highly recommend drawing this curve while you're doing that kind of problem and literally doing what I've done here, which is show the equation for the energy associated with each segment and doing each one separately, and then you just add them together to figure out the amount of heat. Similarly, if you start with the vapor, you can figure out how much energy you have to take out, or how much energy would be released going from steam all the way down to ice, say, or something like that at a given temperature. Okay, so I think that's what I wanted to say about intermolecular forces and phase changes, the Clausius-Claperyon equation, and heating curves. I hope you found the video useful.